In this video, we will discuss about last step of simulation, and it is solving and post-processing. That how we can set up our solution and we can solve our simulation model. And using a post-processing tool, we will interpret our FEA result and check the performance of our product, that how it is going to behave in real world operating condition. So solving is all about to identify that what type of problem we need to resolve, that structural, thermal or NVH type of problem, and to investigate the performance of our product we also need to know that what type of result can help us to check the performance of our product. So in Simcenter we have different type of solutions such as structure and thermal type of solution. So if we want to check structure performance of our product, we can do linear static analysis. If person want to check the resonant frequency, they can perform a normal mode analysis. The person who are dealing with the NVH type of problem, they can do the frequency resonance analysis. So here you can see that solution setup dialog box can help us to manage solver analysis type and solution type as per our requirement. It also enable us to request the output result as per our requirement. In our case, we need a displacement, stress and reaction forces result to check the structural performance of aluminum cover. So in demonstration 4 we will set up our solution, and after solving using a post-processing tool we will interpret our FEA result and we will check the performance of our product, and how it is going to behave. Let's start a demonstration 4. Here you can see that constraint and load are inactive because we haven't created a solution yet. So let's create a solution and name it as a design start. I will keep a Simcenter Nastran as my default solver. You can select the type of solver as per the type of analysis. What about the person who are using a third-party solver such as ANSYS, Abacus, LS Dyna? So they can use as per the availability of their solver. So in our case it is a Simcenter Nastran, so let's select it, and we are going to perform a structural analysis. So it is look good, so let's select it. Here we have a different type of solutions such as we can use SOL 101 for linear static. If we want to do the frequency analysis, then we can use SOL 103 type of solution. If we want to do the buckling analysis, then we can select SOL 105 type of solution. In our case it is a linear static, so let's select it and create a solution. We will keep most of the solution parameter as default, so software will check the geometry by default. If you don't want to check it, you can select none. So I'm going to keep it as default, and in a case control you can also request the output result as per your requirement. So let's preview that the software will by default give us a result of displacement, reaction forces and stresses. What about we need to add or require other type of result? So here if you need a bolt result, then simply by enabling a bolt result request you can add into the output request. The person who are doing thermal analysis, they can request a temperature result. In our case we need a displacement result, so it is by default requested by a software. Same as another important result in our case is stress, so it is already added to output request. I also need a strain result, so I can add the strain result to output request. So let's preview that what we have added is added to our output request, that we just added a strain result, and now you can see it is added into the output request. So it is look good for us. So let's create a solution and add created constraint and load to our active solution. So we have graphical preview that all the load and constraint what we define it added to our solution. So let's solve our solution. Another important thing is that you can also request a unit in output file as per your requirement. If you have a British customer, then you can request a British unit into the output file. So you can manage as per your requirement. So let's solve our simulation model, and it will take some time. So this way the Simcenter help us to set up our simulation model very faster and easily, and we can get our FEA result as much as faster, so we can check the performance of our product and reduce the time of design development by doing simulation at the earliest stage of design cycle. So our solution is done, and let's interpret our FEA result using a post-processing tool. So first we will going to interpret our displacement result and you can see that maximum deformation taking place within the aluminum structure is about 1.472 millimeter, and what you are seeing in graphical window, it is exaggerated result. So if you want to check the actual displacement, you can right away check it. So actual displacement happening within the aluminum cover is available in graphical window, but for the better visualization that which way my product is going to deform, I am keeping the scale about 5. So it's look good for me. So let's move toward another important result, nodal and element von Mises stresses. So here you can see that maximum stress generated within the structure is about 437.11 megapascal, and we can also annotate that where is my maximum and minimum magnitude of stress. So here you can see that around the sharp edge or sharp curve we have the maximum stress, that we know that sharp curve lead to the higher stress concentration. So the maximum stress develop around the sharp edge, and it is also mentioned that which node and which element has a maximum stress. So by reviewing the stress result, we can say that maximum stress developed within the structure is higher than what it should be. Basically, the aluminum material has a yield strength about 300 to 350 megapascal, and we are getting higher than that. So our product is going to deform plastically. Means we have to make changes to our design. So let's get back to the simulation environment and create a clone of our original result and rename it as a design update. So I am keeping all these parameters same as original design. So let's hit OK and let's go back to our idealized part, that we have to make changes to our design to meet specific requirement or specific performance requirement of our product. So using the synchronized technology, we can very rapidly and easily make modification to our design. So I'm going to check a radial dimension of this plant and it is about 9, but I need a 20 millimeter of radius of this plant, and that's it. Okay, so it is look good for me, and let's move forward to the FEM model, that what we have make changes to our design is updated to our FEM model. So what we created mesh is associated with our CAD design. So you can see that something look like that. We have to update our mesh. So let's update our mesh. So this way our mesh is automatically update because we have built a mesh associated with our CAD geometry. Same as let's go to the simulation environment, and you can see that load and boundary condition is automatically update to our new design. So it is the benefit of creating or defining everything associated with CAD geometry. So it reduced the rework of creating a simulation model and mesh again. So this is look good for us. So let's solve our new design and check the performance of our product. That updated design is going to meet a specific requirement of our performance or not. So this way, using a Simcenter, we can develop our product very faster, and we can optimize our design right away by interpreting our FEA result. And we will also see that how we can compare our model or board design in a Simcenter. So let's review the result of our new design. Now let's get back to the pre and post processing environment and load our new result. So let's see the displacement shows that maximum deformation taking place within our aluminum cover is about 1.336 millimeter, and which is less than our original design. So it is look good for us. So let's review the trace result. So one mysis traces tell us that the maximum stress generated within aluminum cover is about 281.98 megapascal, so which is well below to yielding strength of our aluminum cover. So it is going to perform well in a real world operating condition. Another important thing and function provided by Simcenter is we can compare different type of design side by side in a two window, as you can see in this graphical window. So I need my original design wall mysis traces into this window and new design traces into this window, and I can also put both window in sync to compare and for better visualization. So you can see that we can compare our both designs side by side. So for better visualization of counter, let's add a more number of stress value. So I need 20 levels of stress value, and I need to specify my maximum stress limit about 150 for a better visualization and for compare to design. So it's look good for me. Let's create OK, and we can also annotate a maximum and minimum stress developed within our design. So you can see that now in new design you can see that we have a low stress concentration area compared to our original design, and it is generating a less stress compared to the original design. So we can conclude by comparing the result that which one is our base design and going to perform well in real world operating condition. So this way, using Simcenter 3D, we can develop or we can build a simulation model as faster as possible, and we can gain better insight to our FEA result to check the performance of our product. This way, Simcenter help you to reduce cost and design development time by doing a simulation at the earlier stage of design cycle. So this is the end of our video series. Thank you for watching the video. For more video, you can subscribe our YouTube channel.